Okay, so this problem comes from problem set 2. This is problem number 6. For a certain experiment, R134A vapor is contained in a sealed glass at 50 degrees C. It is desired to know the pressure at this condition, but there are no means for measuring it since the tube is sealed. However, if the tube is cooled to negative 12 degrees C, a small droplet of liquid is observed on the glass wall. What is the pressure at 50 degrees C? So let's just start with what we know. Okay, what information are we given? So we know that we have refrigerant R134A is contained in a sealed glass. Contained in a sealed glass, right? Meaning it's going to be, if it's sealed glass, that means there's nothing going in, there's nothing coming out. We're dealing with the same mass and the same volume throughout the experiment, right? So that means we have constant volume and constant mass. Therefore, we have constant specific volume. Right? Because specific volume is just volume over mass, right? So that means V1, specific volume 1, is equal to V2. Okay? At state 1, all we know for sure is that our temperature is 50 degrees C. We know that we're containing vapor. Okay. Then it's cooled down to state 2. And they're telling you, okay, its temperature 2 is negative 12 degrees C. And it says that at negative 12 degrees C, a small droplet of liquid is observed. A small droplet of liquid. What does that mean, a small droplet of liquid? What it means is that you have saturated vapor. This is the very point in time, the very instance in time in which you have, it just begins to become a two-phase saturated liquid volume mix, liquid vapor mixture, right? Over here, we started out with superheated vapor. This is superheated vapor over here. We cooled it down, and now it is just beginning to become saturated. It's just beginning to become two-phase, and we have saturated vapor. That means that X equals 1. The quality is equal to 1. Okay. And that's it. And now it's our turn to figure out the rest of the stuff. Okay, so I know that at state 2 I have saturated vapor. I know that the temperature is negative 12 degrees C. So let's start with looking at the table for saturated R134A. Okay, so I'm looking at table A10, properties of saturated refrigerant R134A liquid vapor mixture temperature table. Okay, so at a temperature of negative 12 degrees C, well, we know that our pressure is 1.85 bars, and more importantly, we know, okay, so first of all, because this is saturated vapor, the quality is 100%. So we know that this specific volume at V2 is going to be equal to Vg, which is the specific volume for just the gas, right? And that is equal to 0.1068 cubic meters per kilogram. Okay. And like we said before, because this is constant specific volume, the V1 equals V2. So over here we also have, it's the same specific volume. 0.1068 meters cubed per kilogram. Okay. Oh, when it asked us, what did it want us to define? It wanted us to find the pressure at state 1. Okay, so now that we have this information, I think we can find out. And we know that we're dealing with superheated vapor at state 1. So I'm going to turn to the table for superheated refrigerant R134A vapor. That's table A12. Okay, so here comes the part where you're going to have to interpolate, because you're trying to find pressure. You're looking for the pressure that corresponds to a specific volume of 0.1068 cubic meters per kilograms, but you're not going to find this exact value. This is very specific. You're not going to find this value in this table. I mean, you might, but chances are you won't, right? So you're going to have to interpolate to find this pressure that corresponds to this specific volume and this temperature, right? So I see here on our table, okay. Okay, so I see here that corresponding to a temperature of 50 degrees C, at 2 bars, the specific volume is 0.12758, okay? And at 2.4 bars, we've got a specific volume of 0.10562, okay? And our current specific volume, the specific volume that we have, is higher than this one and lower than this one. So we know that our pressure at state 1 is going to be somewhere between 2 and 2.4 bars. In order to find the most accurate value, we're going to have to interpolate. Okay, so this is what you do. I'm going to do this pressure minus this pressure over this specific volume minus this specific volume. Okay, I'm going to set that equal to this, our unknown pressure, minus this pressure, over our specific volume minus this specific volume. Okay, so now the rest is just algebra, okay? All right, so this 2.4 minus 2, I'll just go ahead and erase this. This is going to be 0.4. Okay, and then this part, this part down here is negative 0.022, okay? And then this divided by this, that comes out to be negative 18.2149 bars over, to forget our units. You know what he says about units. Meters cubed over kilograms. Okay, so and then I'm going to go ahead and subtract this part. If you have a calculator, you can do the same. This comes out to negative 0.0208 meters cubed per kilogram. Okay. And then you want to get rid of this fraction, right? So what we do, we just multiply both sides by negative 0.0208 meters cubed per kilogram. Okay. This cancels, these units cancel, and then this times this is this comes out to 0.3785 bars. Okay. Okay, and then the last step to find P1, and you just had to add 2 to both sides. That gives you P1 is equal to 2.3785 bars. And is that right? It looks right. Okay, I hope that was helpful. If you have any questions, let me know.